Today, our focus will be on a crucial statistical concept known as autocorrelation, which is particularly important when we are analyzing time series data. As is our customary practice, we will then proceed to apply this theoretical understanding in a practical manner, utilizing the valuable resources and tools available on the Finance ResearchGate website. However, before we delve into the practical application, it is absolutely essential that we first thoroughly understand the underlying mathematical principles. With autocorrelation, what we're essentially trying to determine is whether the previous data points or lags from the past are truly having a significant impact on the specific value that we are observing right now. And if this is indeed the situation we are facing, then we must determine how far back into the past we can realistically go in order to accurately predict and truly understand the influence on the current observed value of this specific variable. So, to facilitate our discussion, let's hypothetically assume that we're dealing with a single univariate time series. This might include things like stock returns, economic growth rates, market spreads, logarithmic prices, or similar data. Autocorrelation, in essence, is a statistical technique used to determine the relationship between a variable and itself. Specifically, it measures the degree of similarity between a given observation in a time series and its past values. This comparison can be extended to include many different time delays, often referred to as lags, allowing for a comprehensive analysis of its historical behavior. So, the main objective here is to precisely identify the specific number of lags, allowing us to clearly understand the connection between the current value and its corresponding past values. It could be just a single instance, and for this specific situation, we're closely examining the connection between the current data point and the one immediately preceding it. And we are performing this operation consistently across every single observation point for that specific variable. For example, this also includes the relationship observed between t-1 and t-2. And so on. Therefore, the relationship isn't just between the current value and its immediate preceding lag, but also extends to the connection between that lag and the value from 2 steps prior. When we consider a single period gap, what we're essentially doing is examining the autocorrelation specifically at a lag value of 1. Following this, we can perform the very same analytical exercise, but instead, we'll be considering a scenario with 2 distinct lags. We are examining the autocorrelation between the current data value and its 2 preceding values. And so on. When we want to calculate the autocorrelation, the initial step involves determining the product of the deviations. Then we proceed to scale that particular result by dividing it by the square of the deviations. So, as an illustrative example, let's consider a scenario where we are presented with this specific time series data. The first thing we do here is find the average. First, we sum all of these values together, and then we proceed to divide that total by 6. This calculation gives us a specific numerical result. Following that, our next step is to determine the individual deviation of every single number from the calculated average value. Therefore, the deviation of this very first number that we have right here, when compared against the mean, is precisely this particular value. The difference between the variable's specific value here and its mean is what we're observing. We then continue this process for all the remaining data points. So, what we are calculating here are the individual deviations. Next, we take these individual deviations and square each one of them, because we are getting ready to calculate the variance. So once we have squared each of the individual deviations, we then add them all together. However, we do not divide the sum by n or by n-1 to find the average of these squared deviations, which is commonly known as the variance. The reason is, we don't have to, since the equation already tells us what to do. This calculation also requires us to determine the average value of the product of the individual deviations. So in this specific case, we are going to divide this entire resulting equation by the quantity of t-1, where t clearly represents the total number of observations present in our time series data. -1 because we are dealing with a sample, and we also divide by t-1 for the denominator. There's no actual requirement to perform that particular action for every single step, because ultimately, those elements will effectively cancel each other out. This is precisely why we avoid dividing by the average, or more accurately, by the total number of observations, given that we'll be performing the exact same operation within the numerator. Once we find the denominator value, so the first thing we need to do is to find the numerator. Now, if we are specifically looking to calculate the autocorrelation at a lag value that is equal to 1, then we'll have to determine the product of the deviations between each individual observation and its corresponding lagged value. So it's quite important that we only consider a single period lag, because we have detected clear autocorrelation specifically at lag 1. We apply this exact same principle here and again here consistently across all of our observations. So the current observed deviations at this specific point are then multiplied by the value of the immediately preceding deviation, and this particular calculation process is continuously repeated across the entirety of the time series data. Once we have finished this, we then sum them up, and the final stage requires us to divide the calculated numerator, which is the product of all deviations, by the sum of the squared deviations. And this particular calculation will provide us with the autocorrelation coefficient at a lag of 1. In this specific instance, we are observing a value of minus 0.24, which clearly indicates that we are experiencing a short-term horizon reversal. It's a fundamental principle that the projected future value will experience a decline if the present valuation is observed to be significantly higher. We can perform this identical process to calculate the autocorrelation specifically at a lag of 2. The primary distinction in this particular calculation is that whenever we engage in multiplication or any other operation using these statistical deviations, we deliberately ensure there's a separation, a gap of 2 distinct time periods. As a clear illustration, think about the interval between xt and xt minus 2. Though, returning to our deviations number here, it's important to understand that we do not simply multiply this value by that one. Instead, we take this particular number and then we apply a 2-lag operation with this other one. This process then results in our single product deviation. Also this one with this one. Or we take this particular value and pair it with this other one, and we continue this process for all relevant data points. Our primary objective is to accurately determine the value of the numerator, and then we proceed to divide that result by the exact same denominator, which is comprised of the sum of the square deviations.
And then we get autocorrelation at lag equals 2. It's also minus.
So even when we consider a very short-term horizon or extend our analysis to an intermediate or even a much longer time horizon, we consistently observe a negative value. However, this particular value is significantly lower than what we found for the very first autocorrelation. Another important concept that you might frequently hear discussed is the partial autocorrelation. A very partial autocorrelation aims to find the direct correlation between 2 points, removing the influence of any intermediate ones. For instance, if our goal is to precisely estimate the autocorrelation at a lag of 2, it becomes essential to control for the influence of any autocorrelation that might be present within the intervening time period. In this specific scenario, we're examining the autocorrelation at a lag of 1. This is because the term that separates xt from xt minus 2 is precisely xt minus 1.
If we control for the lag value, what will be the coefficient here which reflects the autocorrelation?
But because we controlled for the autocorrelation at lag 1, then we call it partial autocorrelation. So for example, if you were to perform this and then run the regression, this specific coefficient would represent the partial autocorrelation at a lag of 2. And notice that here it's higher than if we don't control for the autocorrelation at lag 1. The reason for this is that if that particular value increases, and considering we have negative autocorrelation at lag 1, it clearly indicates that this specific value will subsequently decrease. Now, if we account for the specific influence of this particular factor, then we should observe a noticeable decrease or a significant reduction in the overall numerical value of xt, precisely of this specified magnitude. If you fail to account for this factor, it implies the presence of a confounding effect, which means that if one variable increases, the other will consequently decrease. And because, when that specific metric or value starts to decline, it's going to have a very beneficial and positive impact on xt, which is important. And as a result, what it does is it essentially helps to counteract or negate the adverse relationship that we've identified as existing between the expression x2 minus xt minus 2 and the variable xt. This was due to an escalating effect, which originated from the decline of xt minus 1 itself caused by the increase in xt minus 2. This outcome will result in a less pronounced negative correlation observed between the 2 preceding time points and the present measurement. This is precisely why failing to account for the intermediate autocorrelation within our analysis led to a lower negative relationship being detected. The actual relationship, when properly considered, is substantially higher in this particular case. So, what are the key statistical measures that are most pertinent here? We've already discussed the boxes pairs, which we introduced earlier in our presentation. And then, of course, we also have the Young box method to consider. The Young box method demonstrates greater robustness when dealing with smaller sample sizes, particularly those considered finer or more precise. This is primarily due to its inherent ability to accurately adjust for the specific number of observations present within the dataset. Consequently, the total count of observations in such scenarios can indeed be quite limited. Specifically, in the context of our current analysis, we are working with a mere 6 observations. So, at this point, we're going to consider the autocorrelation value at lag 1, which we previously calculated. First, we take that value and square it, then we divide it by the quantity t minus 1. The fundamental reason we incorporate this minus 1 adjustment is because we are effectively sacrificing a single degree of freedom due to the nature of a 1-lag autocorrelation in our calculation. However, in this specific scenario, the situation is more complex as we are actually losing an even greater number of degrees of freedom. We'll require 2 values. Why is that exactly? Because we're looking back 2 periods in time. And if you are able to if you are truly able to, if we carefully count the precise actual number of all these observations that we have gathered here, it will clearly be 4. For instance, right here, we can see that we have 1, then we also have 2. Following that, we have 3. And finally, we have 4 distinct points. This particular value, which we are currently examining, is equivalent to the expression t minus 2, and when we calculate that, it is 6 minus 2, which ultimately equals 4. These are what we refer to as the degrees of freedom. And the same principle applies right here. Following that, we then proceed to multiply this by the variable t, and subsequently, we multiply it by the quantity t plus 2. And that calculation will ultimately provide you with the desired outcome. Which is always positive. That's the reason why we are squaring. Now, because we are performing a squaring operation, it becomes absolutely essential that we then take that resulting number and carefully compare it against the well-established chi-square distribution. This is fundamentally important because by its very definition, the chi-square distribution represents the sum of several independent squared standard normal variables. It's important to remember here, this is a standard normal number because we divide it by the denominator, which is the square deviation. So we scale it, we standardize it. So, the fundamental principle here is that whenever we're working with a variable that's a squared standard normal, we must then apply the chi-square distribution. The degrees of freedom in this specific case are 2, precisely because we possess 2 squared standard normal variables, namely this one and also this one. So, if we consider this particular value, which is indeed greater than 0, it suggests that we might potentially have some autocorrelation present, but it's specifically quite weak because the p-value associated with this number is notably high. It's quite high, much higher than 5%, which clearly indicates that the probability is substantial. The evidence supporting the idea that this particular value originates from the chi-squared distribution operating under the conditions of the null hypothesis, which specifically posits that there's no autocorrelation present, is quite compelling and robust. So, based on our observations, the data actually aligns with the null hypothesis. This means we simply don't have sufficient statistical evidence at this point to confidently reject that initial assumption. Alright, so now let's proceed to apply the autocorrelation. We'll be utilizing the Finance ResearchGate website for this particular task. First, we need to carefully select the appropriate time series data that we want to analyze, and then, for the purpose of this demonstration, we'll set our start year to 2000, and the end year will be 2010. It is time for us to make a selection regarding the variable monthly return. For the purpose of this demonstration, let's just select a single ticker. We'll specifically search for the company Apple. And then we can now apply it. For this specific analysis, we currently only have one firm in our time series. We could, however, construct an index such as a collection of companies that all belong to the very same industry sector. We'll be calculating the mean, but in the end, what we'll have is a time series variable. This means there will be one observation for every single time period. In this particular scenario, there is no necessity for us to aggregate the variable data points, primarily due to the fact that our current focus is exclusively on analyzing the performance of just one individual firm. As you continue to scroll further down the page, you will find a comprehensive display of all the monthly stock returns. What you are observing here represents the fluctuating value of the stock over a period of time, specifically for the company Apple. If you take a look at the graph displayed here, you'll notice the returns fluctuate, moving up and down in certain periods. You might even see negative figures, which is completely normal and expected in the stock market. At other times, you might see positive or even quite large positive values. So it clearly fluctuates throughout the time period. The main question is, can we then have an autocorrelation? What this implies is that if we observe a significant autocorrelation, then we possess the ability to quite readily forecast the subsequent period's rate of return for the Apple stock. And if we are able to achieve that, it means we have a clear investment opportunity. We can certainly make money, assuming the transaction cost is quite small. Alright, so now, to effectively test for autocorrelation, what you'll want to do is just scroll down a little bit here. You'll notice we have a very specific dedicated section where we can test the autocorrelation looking back up to 12 months. So we're examining lag 1, and then the autocorrelation at lag 1, lag 2, and continuing all the way up to lag 12. The total number of observations available to us is 132, which effectively spans a period of nearly 10 full years, or perhaps 11 years, with 12 months of data for each observation. As a result of this analysis, you will obtain a comprehensive total of 132 observations concerning Apple's monthly stock return. Regarding the M parameter, we are currently testing the lag values, specifically up to a maximum of 12. And for this analysis, we're utilizing two distinct tests, the Box-Pearson and the Young box. By the way, the Box-Pearson test is quite similar to the Ljung-Box test in terms of its mathematical formulation. However, there's a key difference in how we apply it. With the Ljung-Box test, we don't scale or divide by the degrees of freedom, but in the Box-Pearson test, that's exactly what we do. Both tests, in this case, do not reject the null hypothesis, meaning that we fail to reject it. This outcome suggests that there isn't enough statistical evidence to support an alternative conclusion at the chosen significance level. We are considering the null hypothesis, which states that the autocorrelation is precisely zero. This implies that we can confidently accept that the autocorrelation is effectively zero, or in other words, does not exist at all. Therefore, to gain a clearer visual understanding of the autocorrelation values, we can observe that here, for instance, at a lag of 1, the autocorrelation coefficient is remarkably small, almost negligible, and very close to zero. So at this particular point, we're looking at a value which is 0.14. However, despite its presence, it doesn't hold much significance for our analysis. Moving on, we can now observe that there are clearly two distinct lines present. So, what we're looking at here are the confidence interval limits. We can then calculate these by taking the value of 1.96 and dividing it by the square root of t, which in this particular instance is equal to 132. This calculation will then provide us with an approximate value of 0.17. Now, if the autocorrelation's absolute value is greater than 0.17, meaning it's either above positive 0.7 or below negative 0.7, then this indicates a significant value that we simply cannot afford to overlook. However, all of the autocorrelation we're seeing falls within this particular range, which means it's not statistically different from zero. If it were to exceed that specific number, it would indicate that we have autocorrelation, but in our current situation, we simply don't. Additionally, we have a table to consider. Again, you'll compare each individual number with a specific benchmark provided here. We are unable to surpass this benchmark, which indicates that we remain inside the confidence interval. This further means we cannot reject the null hypothesis, which states that the autocorrelation is effectively zero. It is actually very close to zero. Even if you were to consider the partial autocorrelation, after we have accounted for the effects of the intermediate autocorrelation, it still remains within the expected range, which clearly indicates that the partial autocorrelation is not statistically significant from a value of 0. So, overall, the monthly stock returns for Apple, specifically from the year 2000 through to 2010, do not present any statistically significant or strong evidence of autocorrelation. That concludes our discussion for today. I truly appreciate you taking the time to listen.